It looks like a wave, yeah, good. We're going to talk about waves, vibrations, and objects that are in something that we consider simple harmonic motion. Okay, so simple harmonic motion. Okay, I'm going to talk through this a little bit. Put it down in your own words. But what you need to know about simple harmonic motion is that it is basically repetitive and identical motion. Repetitive and identical motion. Okay, so anything called simple harmonic motion is characterized being very repetitive and very identical or symmetrical or near identical. They use this object bouncing back and forth on a spring. And we don't see that example a whole lot in real life, right? We don't see this object set up on the end of a spring and bouncing back and forth. Not a super real life example, but something that we do see a lot is something called a pendulum. Okay, do you know what a pendulum is? What's a pendulum do? Yeah, it just swings back and forth, right? And does the pendulum theoretically ever stop swinging back and forth? No, theoretically no, right? That has to deal with the conservation of energy, which we just got done talking about, right? When we pull a pendulum up before we release it, what type of energy does it have? Potential. As it swings through its kind of base at the bottom, what type of energy does it have? Kinetic, right? So there's this transfer of energy throughout that pendulum swing that you'll see is hopefully conserved, right? The only thing that would slow a pendulum down would be friction upon its axis point, right? That's about it. But a pendulum is considered simple harmonic motion because it's very repetitive, right? It swings back and forth. It's what you use to get hypnotized, right? Has anybody ever been hypnotized?
I've tried to, but I haven't gotten it yet.
It didn't work. So this pendulum is going to be something that you see swing back and forth, repetitive, identical, symmetrical motion. Where else do we see pendulums in real life?
Clocks.
Yeah, clocks, right? Grandfather clocks have that big pendulum that swings. Why is it really important that the pendulum motion is repetitive and identical in a clock?
Keeps the time.
Yeah, otherwise it's not going to keep the time, right? It's got to be repetitive and identical in order to keep that time. Okay? So an object that's in motion, the actual object that's swinging back and forth or bouncing back and forth or vibrating back and forth, that's what we call a simple harmonic oscillator. Okay? A simple harmonic oscillator is going to be the object itself that is going to be in motion. Okay? And then we're going to deal with looking at waves, which are considered simple harmonic motion, and we're going to deal with vibrations, which are really small waves. But vibrations are obviously considered simple harmonic as well because they're repetitive and they're symmetrical, right? It wouldn't be a vibration if it went, all over the place, right? It's repetitive and symmetrical. Okay. So I want you to take a look at this example given right over here on the side. You'll see this kind of example a lot used in books and in problems, things like that. But there's a mass on the end of a spring. Okay, at this point right now, is the spring stretched or compressed or static? Can you tell? It's not compressed, it's not stretched, it's going to be static. Okay, it is in the static position because it tells us right under here x equals 0. Okay, so that means the displacement of this mass is 0. It's right at its resting point. Okay? Here, as you see, it pulled, right? It says our x is greater than 0. It doesn't give us an exact value, but it tells us our object is being pulled, right? Here's our original point. Here is our new mass, which means there's some displacement here of our string, so there's been a stretch. So what type of energy does the spring have at this point? Potential or kinetic or both? Potential, right? As I stretch my spring, what's it have the potential to do? Snap back, okay? I thought you guys would be a little quicker on that one. Okay, on the next one right below it, when it's compressed, what type of energy does it have? Potential. It has the potential to spring back. Okay, are we not seeing that? Or is it just because it's Monday morning? A little of both. Okay. Anytime we have the spring out of its static position, it has to be potential energy because it has the potential to move back to its static position. Okay, so no matter if it's stretched or compressed, anytime it's out of its static position, it's got to have some form of potential energy. If it's in motion as well, it would have both types. Right? This chapter is going to connect that those energy concepts to simple harmonic motion as well. So don't think that just because we're done with the chapter, you get to forget everything you learned there. Okay, we're going to have to apply that stuff this chapter as well. All right, so we have lots of vocabulary that goes with this chapter. Okay, would you rather have them all at one time or one by one? Okay, I'm going to give you time to write them all down, then I'm going to briefly just kind of go over some highlights, okay? There's a lot. Okay, so I'm going to give you 2 or 3 minutes to get these written down, and then I'll talk through a little bit more about what we're looking at. Talk over these just a little bit to give us a better in-depth look at kind of each of these vocabulary. An oscillation or a cycle means any type of simple harmonic motion that goes back, forth, and back to its center. Okay, so when we think about an oscillation or a cycle, picture a pendulum. Okay, if I have a pendulum here that is in its base state, right, and I pull it up here, it would swing up, back, and back to its center. Excuse me. Thank you. It would swing forward, back, and back to the center to complete one oscillation. Okay, so if you think about a pendulum in a clock, it's not just to and fro, right? It would have to be back, over, and back to its beginning to be one complete cycle. Okay, the same goes for a wave. We'll look at waves here a little bit more specifically, but you always have to get back to your starting point to be considered one oscillation, okay, or a cycle. Displacement is our distance measured from an equilibrium point. Usually that's only going to be applicable when we talk about springs, right? Waves have a different way to measure our distance. Period is the time for one oscillation. Have we talked about period and frequency before? Yes, we have. Okay, so hopefully those are ringing some bells. They're coming back to us. But period, remember, is a T, so it stands for time, right? It's the time it takes to make one revolution or one oscillation or one vibration, whatever it is. And what should that be measured in? Seconds. Okay, it should be measured in seconds. Okay, most of the time. Amplitude is what we consider the maximum displacement that a spring could reach. It's still going to be a displacement. Okay, so I'm still most of the time just going to use x for that variable if we're solving for displacement. Just because it's the maximum, it doesn't change anything in terms of us solving for it. It just means that's the max that it can be stretched or compressed. Okay, frequency is oscillations per second. Okay, so we measure this in hertz. That might be a little bit new from the last time we studied frequency, but the unit for frequency is hertz, and that means oscillations per second. Wavelength is the distance between successive features of a waveform. So identical spots to identical spot on the wave, and we're going to look at that in a little bit. But wavelength should be measured in meters. And the last thing is speed or velocity, which is the velocity of the wave or the velocity of the object in motion. Okay. So we're going to look at a wave here a little bit closer right now. When we look at a wave, okay, we see that this is kind of our middle axis right here, okay? And when we look at a wave, our amplitude, it's not just having to do with springs, but our amplitude is our maximum height. This would also be equal to the maximum kind of depth of that wave, okay? So these two values would be equal to each other. Right, amplitude, since these waves are identical, right, it's got to be repetitive, identical motion, the amplitude up has to be the same as the amplitude down. Okay, does that make sense? The wavelength now is when we either go peak to peak, or trough to trough, or center point to center point, right? We see the wave go all the way down and all the way back up to get to its starting point. That would be one wavelength. Okay, does that part make sense? So wavelength, you got to think about the fact that it's going to start here. It's going to go all the way down, all the way up, and back to its starting point. That's one wavelength. That distance right there is one wavelength. Okay, a lot of you will try to shorten that up or make it look a little bit differently, but our wavelength is not just when we get back to our starting point. We have to go past it and back to an identical portion on the wave. Okay, a lot of you will cut that short and try to say that this right here is the wavelength. That's not the case. Okay. All right, so we're going to review the difference or the connection between frequency and period. You guys have this equation, but you might want to put it down on this chapter's equation sheet. That's up to you. We know the relationship between frequency and period. Now we're going to be able to connect the velocity the wavelength and the period or frequency of a wave. Okay, so we're going to tell how far it's traveled in this certain time. That would give us the velocity. Okay, and here's our equation to do that. All right, does anyone know what this Greek letter right here is called? Yeah, lambda. That's lambda, and that stands for wavelength. Okay, wavelength is measured in meters. Period is measured in what? Seconds, and meters per second always gives us velocity. Okay, that's where that comes from. Okay, wavelength is how far that wave travels. Period is how fast it took us to travel one wavelength. So that gives us our velocity. Okay. If we're given frequency and we need period to go in this equation, we can just use this to help us swap those. Remember, frequency and period are just reciprocals of one another. Okay. Any questions so far? Yes. This visual on the left shows us now another connection in terms of energy types, potential and kinetic energy, or both. Okay. So, if the mass on this spring, right, we're back to springs, if it's stretched or compressed to its maximum, which is called the what? Anyone remember? It's a capital A. Amplitude is its maximum displacement. Okay, stretched or compressed to its max is called the amplitude. So if a spring is stretched to its max, it would have only potential energy, right? We're compressed here to its max. That's why it says negative A. Okay, that means it's negative amplitude, so it's stretched all the way, or it's compressed all the way to its maximum. Why is it negative? Yeah, it's going backwards, good, or to the left, right? It's being compressed. Negative A. So when it has potential energy, what's the equation for potential energy of a spring? Anyone remember? Good. Good, 1/2 kx squared. And in this equation they gave us right up here, they said 1/2 a squared. They're just saying that since it's the amplitude, right, I'm not going to have you change that variable. You just got to understand that x could be the amplitude or it could just be the regular displacement. Okay? So I would, if you want this equation again on this chapter's equation sheet, I'd go ahead and put it on there. You're probably going to use that. You're going to use those conservation of energy equations again. Okay, so if you want to transfer them to this equation sheet, you can. Otherwise, you can just get out your equation sheet from last chapter too. Okay. All right. So when it's stretched or compressed to its max, it has all potential energy. If the mass is at the equilibrium point, right, if it's moving, but it's still at the equilibrium point, it's got all kinetic energy. So do we see how this indicates to us that it's in motion? Can we see that on that picture or not so much? Okay, these little lines here kind of tell us that it's moving, right? It was compressed all the way here, then it was released, and it's now moving through its equilibrium point to reach its stretched amplitude, right? Does that make sense? Okay, so as it's moving through that equilibrium point, it still is in motion, so it's got what type of energy? Kinetic. And it's at its equilibrium point right now, which means it's got no potential. Okay, so at this point, we've got all kinetic energy. If it's at the turning point or it's at its amplitude, right, it's at its now stretched maximum, it's got all potential again. Okay, so do we see that sliding scale happening here with the spring instead? Okay, we talked about the roller coaster sliding scale in terms of energy and kinetic and potential. Now we're looking at with the spring. Okay, and I want to look at this last visual right here. Okay, it's gone from its compressed through the center, now it's at its amplitude on the other side, and it's on its way back. So it's somewhere here in the middle at an x displacement. We've got both types of energy here, potential and kinetic. Okay, does that make sense why that is the case? Give me like a yes or a no. Okay, it is being pulled back to its equilibrium point, but it's not there yet. So it's still a little bit stretched, which is why it has potential energy, and it's in motion, so that's why it has kinetic. Okay, so at that point it's got both. So now we're going to look at the equation for finding period and frequency of a spring. Okay, we looked at the way we find period and frequency of a wave using the wavelength and using the velocity. Now we're going to look at finding period and frequency of a spring. Okay? So period of a simple harmonic oscillator does not depend on the amplitude, how far it's pulled or how far it is compressed. Okay, it doesn't matter about the stretch or the compression of the spring. What does matter is the spring constant, which is like the stiffness of the spring or how tough the spring is. Okay, that gives us the amplitude. I'm sorry, that gives us the period or the frequency, not the amplitude. Okay, so these are two equations. You're going to need both of these on your equation sheet. Spring constant are? Anybody have an idea? No. K is newtons divided by meters. Okay, newtons divided by meters. And that comes from this equation. Force equals K times X. Okay, this is newtons, K in meters. So if I want to solve for K, I would divide that over. Okay, so if we're solving for K, it's newtons over meters. All right, let's try one here. Okay, period means we're solving for T or F. T. Okay, so T equals 2 pi square root of M over K. Is that right, or did I invert those? That's right. Okay, is mass measured in kilograms? Is that what it's supposed to be measured in? Yes, mass has to be in kilograms. Okay, so we're good to go. So T equals 2 pi times square root of 0.6 over 80. Okay, so you solve inside the square root first, then work out. Okay, Andy, tell me what you got.
For the first part, 0.086.
Okay, 0.086 right in here. After the square root. Is that after the square root? Okay, then you take it times 2 pi. And what do you get?
0.54.
Perfect. 0.544. And what's our units here? Seconds. All right, very good. Questions here? Okay, with these two problems, whenever we multiply by 2 pi or divide by 2 pi, we have to just be careful in terms of if we use parentheses or if we divide by 2, divide by pi. This one was simple because we were just multiplying, so it didn't make a difference. But on these problems, we got to be careful if we're going to move that 2 pi over. You just got to be thoughtful with the algebra that goes into it. Okay? Any questions here? Okay, so that means in order for the spring to go out, back, and back to its original position, it takes about a half a second. Right, 0.544 seconds. Okay, if we're unsure of the K value, if we're unsure of the spring constant in order to put in that equation, we have kind of another way to go about that. And it comes from this equation, force equals K times X. I think we've seen this equation before also. Okay, and what this means is that the force that is applied to move this spring a certain distance, X, would give us our spring constant, right? So whatever force we apply to move that spring a certain displacement, that's going to give us our K value, okay? So this works well for horizontal springs right here. If it's vertical, what's usually moving the spring if it's hanging vertically? Gravity is usually moving the spring. So what would our force be? The force due to gravity. Okay? Sorry, do we have what we need there? Okay. Okay, so if it's a vertical spring, we would use the force due to gravity to solve for K, right? Here's our static spring right here. We add a mass to it to get it to stretch this distance, whatever this distance is, x. And to solve for our spring constant, we would move x over. We would take force of gravity divided by that displacement would give us our spring constant. Okay? So we're still using F equals kx. This is an equation that should probably go on your equation sheet. If it's vertical, we might use Fg equals kx, right? Which is really mass times gravity equals kx. Okay, any variation of these equations can go on your equation sheet, whatever you feel comfortable with. Okay, a family with a mass of 200 kilograms gets into a 1,200 kilogram car. What's the car's spring constant if the springs compress 3 centimeters? Okay, so let's start thinking here. We want to solve for K. We could solve for K using the period or the frequency equation, but do we have the period or the frequency of these springs? No, which leads us to using that F equals Kx equation. F equals K times X, because we do have the displacement, which needs to be converted to meters, right, which is 0.03. Right, 2 decimal places from centimeters to meters. So let's think about this. When the car is at rest, what is there any compression of the springs when the car's at rest? Should there be theoretically any compression of the springs? No, right? Hopefully the car is built so that the springs are meant to withhold the mass of the car. Right? Does that make sense? There shouldn't be any compression in those springs when the car is just at rest, when nothing is in it, right? So what mass is going to be compressing these springs? Just the mass of the people, right? It should be built well enough that the springs are not being compressed by the weight of the car itself. So it should be just the people that are compressing it. So when we say F equals Kx, this is a vertical spring, right? It's a vertical compression. So we would say mass times gravity equals K times X. We're using just the mass of the family times 9.8 equals K times our compression. Okay, does that make sense why that is only the mass of the family? Right, the weight of the car should be enough to kind of keep it in place, okay, or in balance. Okay, so are these springs pretty tough or pretty lightweight, I guess? What do you think? Pretty tough, right? The spring constant is usually relatively in the hundreds, low thousands, for everyday type things. These are pretty tough springs, okay? Like a slinky would be, I don't know, a very low spring constant, right? The tougher the spring or the stiffer the spring, that means the larger the spring constant. Okay, so this is a pretty large spring constant. Any questions? Everybody get that to come out okay? Okay. How far will the springs compress if the added mass was 300 kilograms instead of 200 kilograms? Okay, go ahead and try this one on your own. How far would the springs compress if the added mass was 200 kilograms instead of 300? 300 instead of 200, I'm sorry. 300 instead of 200. Okay, does the spring constant of these springs change? No, the composition of the springs doesn't change. So you're going to use the spring constant you just found to solve a new question. You could keep it in meters, that's fine. I put it back in centimeters to show us kind of that true relationship. Right, so it increased by 50% and the mass increased by 50%, right? So that relationship is true. Direct. Tell me one more time. You had 0.045? 0.0. Oh. In terms of units. Okay, hertz is fine. That's what we want frequency in. Grams need to be in kilograms. So we go 0.00015 kilograms. All right, we're moving that decimal 3 to the left or dividing by 1,000 to get to kilograms. All right, so we want to use which equation here? The one for frequency, right? The one that has K. So it says frequency equals 1 over 2 pi square root of K over M. Okay, so this is going to take a little bit of algebra to get K by itself, right? So let's go ahead and just start that. I like to plug in my numbers before I rearrange the equation, but that's up to you. That's 0.00015. Okay, so algebraically, the first thing that we should do is multiply by 2 pi. Good. And here it doesn't matter if you use parentheses or not because you're multiplying. Right? When you divide by 2 pi, then you got to be really careful. We're multiplying it over because it's in the denominator on the right side, so we need it to be in the numerator. Multiply it over. That gives us about 25.13. Hey, I'm really going to keep this in my calculator, but I'm rounding on the screen. Okay, once we're to this point, what's the next step algebraically that we're going to have to do? Good. Square both sides. So we want to get rid of the square root by squaring both sides. Oops. Okay, and if I do that, that gives me about 631.65 equals K times, K over 0.00015. Okay, last step where you're going to multiply that up. Good. So K equals 0.095. Okay, did we get that to come out? Okay, very good. Look how much smaller this spring constant is in comparison to the car one. right? This is less than 1 Newton meter. So that spring constant is very soft, right? That spring is very soft, which makes sense because it's a spider web, right? It's not built of anything too tough, okay? All right, good. Last little part you're going to do here on your own. What frequency would the web vibrate if the insect were 0.5 grams instead of 0.15 grams? Okay, so you're taking that spring constant that you just found. You're going to put it into this other equation to solve for frequency.